Hi guys, let me share my screen. ஸோ ஐ திங்க் நேற்று நம்ம அரே வரைக்கும் பார்த்தோம். யூடியூப் போய்க்கலாம்.
starting index, and in the next part we have the ending index, and then we have arrays. As I said, arrays are a collection of same type of data types. Okay? That is the one line explanation of arrays. So what we are doing here, we are declaring an array which has this type. It is a string and it can have two items. So this part, this two part, this is basically the size of the array. So when we say toString, when we say this, we mean this array is of the array also. So this size is created by Go, which are called slices. And this is how we can make a slice using an array. And if we try to run this, we get this result of 3, 5, and 7, because this syntax, this indexing syntax that we use to slice, to create a slice out of an array, this is how it works. In the first part, we have a opening square bracket. In the first part, we have the starting index, and in the next part, we have the ending index, and this is excluded. This is not part of it. So since the starting index is 1, we start from here, and the ending index is 4. So 0, 1, 2, 3, 4, and we exclude it. So this is the range 3, 5, 7, and that's what gets printed here, 3, 5, 7. Now a slice is a very special data structure that is available to us. It is very flexible and it is very useful, and its mechanism is a little different than our typical arrays. And slices are also called a reference type. They are called a reference type because a slice has always some backing array. A slice only refers to an array that is working in the background. So if you want to understand how it all works, let's imagine this. We have an array. Let's see. This is the array. And we have different indexes of the array. And let's say we have numbers 0, 1, 2, 3, 4, 5, 6. Now this is an array in Go, and its type will be the first part 1, 2, 3, 4, 5, 6, 7. 7 integer. This is the type of this array. Okay. Now, if we create a slice, now how slices work is a slice has 3 parts to it. So you can imagine a slice. We have a slice, and a slice has 3 parts. One is the length of the slice. Second, its capacity. We'll come to capacity soon. Capacity. And the third is a pointer. And a pointer to the first element of the array, or a pointer to the first element of the array that the slice is pointing to. So in this case, it does not have to be 0. It can be this also. It can be 2 also. So now a slice, when we have a slice, it has a background array, and this slice points to this element. So this first element of the slice is 2. Now the capacity of an array, the capacity of a slice is basically starting from the element the slice points to up to the last element of the backing array, not the last element of the slice. So in this case, the capacity can be 1, 2, 3, 4, 5. The capacity is 5, and the pointer is 2. That's what it points to. And what is the length? Now length can be the same as the capacity depending on how we sliced it out of the array, or it can be different than capacity. So in this case, length can be, let's say, 3. Capacity can be 5. Length can be 3. Length can also be 5. Now it's all a little confusing. Now we will see a couple of examples and it will become more and more clear. I've just shown the figure here so that we can come back to it and we can imagine and visualize how it all works. Okay, so let's get to the example first. Now here we have an example. We have an array. We have an array, not a slice. We have an array whose length is 4. Now let's picture this. Let's picture this here. We have this array. Okay. So let's picture this. We have an array like this. Okay. And these are the elements. So we will start the indexes from top to bottom, 0 to 3. Okay. And in the first index, we have John. In the second index, we have Paul. Third, George. And then we have Ringo. Okay. This is 0, index 0, this is 1, this is 2, this is 3. This is the array that we have. It is a fixed size array. We cannot expand it. We cannot reduce it. We cannot do any kind of changes to it. But we can slice it. Now let's understand how slices work. In this example, what we are doing, we are constructing a slice A, and it is slicing from this array from index 0 to 2. So now the slice A will have 3 parts, as I said. First part is the length. Length will be, since it is slicing from 0 to 2. So let's say 0, 1, 2, 3. 0 to 2. And since we exclude the last part, so the length is 2. Okay. And second part of the slice is capacity. You'll be more clear about the capacity after we go through some examples. For now, let's just stick to the concepts. Now the capacity, as I said, is starting from the first element of the array that this slice points to, which is 0, up to the last element of the backing array, not the last element of the slice. Now, how much is the capacity? The capacity is 4. Since we start from the first element, the capacity is the same as the backing array. Now we have the capacity 4. And we have a pointer. It has a pointer which points to John. Basically, this part, John. Okay. Now we have A. In the same way, we have B. B, what it does, it starts from the second index, basically index 1. Now we have length as, it starts from this index, and it goes up to the last index, third. And since you exclude the last one, the length will be 2, the same way. And the capacity is starting from the first element of the array that it points to up to the last element of the backing array. Now the capacity is 3. And the pointer is, what is the element that it points to? Is Paul. Okay. This is how the physical representation of an array and the slices that come from it looks like. Okay. Now, in this example, what it is trying to do is it is doing in the array, in the slice B. In the slice B, it is changing the first index to XXX. What is the first index of the array B? Since it starts from here, it is changing. It is trying to change the first index, the value of Paul, this part, to XXX. So now the value of Paul has been made XXX. Okay. And now we are printing A and B, and we are also printing the backing array. Now let's understand why are we looking at this example. Since we know slice is a reference type, and now you understand why do we call it a reference type. We have an array which is a fixed type, and we cannot expand it, and but we can slice from it. So we have two. Now this array, the array names, the slice A, the slice B. All three of them point to the same thing. All three of them have the same value. Names is the actual data type, and the slice A and B point to names. They are sliced from it, but they point to the same data. That's what you have to understand. A slice does not have the data for itself. It points to an array. It points to a backing array. In this case, all three of them have the same value in this position, which is Paul. And now any of them. So in this case, B has tried to make this value as XXX. Now what happens? This will change for all of them. This will change for all of them, A, B, and names. Now, if we run this, let's see what we get. Let's clear this and try to run this. You can see in the first print statement here, in the first print statement, we are getting John, Paul, George, and Ringo. And after slicing, we are printing the value of A and B. And the same way, we have John and Paul and George. Okay. Nothing has changed up till now. The moment B has changed the value of Paul to XXX, now we have printed A. Now A has John and XXX. We have printed B. B has XXX and George. And we have also printed the names. There's John, XXX, George, Ringo. Now this, since one of the slices changed the value in that index to another value, that value got reflected in all three of them. The backing array that contains the data, and all the slices that point to that array. Okay, that's the point that this example is trying to make. Whenever a slice which is pointing to some array changes some value in that array, the value of the arrays changes, and all the values in all the slices that are pointing to that array, they also change. We don't always create slices out of an array. We don't have to declare an array and slice from it. We can directly create a slice. Go provides us the ability to directly create a slice, and in the background, Go will create a backing array, and B and names. Now, the moment B has changed the value of Paul to XXX. Now we have printed array, the backing array that continuing to some array, changes some array and slice from it. Create slices out of an array. We don't have to declare an array and slice from it. We can directly create a slice. Go provides us the ability to directly create a slice, and in the background, Go will create a backing array and it will give you a slice which points to that array. Okay, and that's how it will work. So this is the syntax using which you can directly declare a slice. You do not have to declare an array and slice from it. You can directly declare a slice, and this is called a slice literal. We are literally declaring a slice in one line. Okay, we have a variable declaration pattern here, the with the colon equals to, and here we are saying it is a slice since there is no number in between the square brackets, which means it is a slice. That is the indication. That is the difference between an array and a slice. In an array type, you will find a number, which is the size, and it is part of the type, and it is a slice of integers. And here we are providing the values during the initialization phase, and here we are printing it. In the same way, we cannot store any other data type in a slice or in an array. It is a collection of homogeneous data types. In the same way, we can also make a slices of structs. So this is how the syntax looks like. You write a pair of square brackets, then you define the type. In the same way, here we have defined the type. You can integer, boolean, or a struct. If it is a struct, you have to provide the type of the struct. And the type of the struct is this. It has two fields, I and B. I is of type integer, B is of type bool. Now, right after, since it is an slice literal initialization of type struct, okay, we have to provide all the values that goes inside this slice of structs. So we can provide, we can follow this pattern. So let's run this and see how it looks like. Okay, and we can see all the slices that got printed here. And this, since this is a slice of structs, we can see all the structs being printed here in the Gos format. Now, another thing is you can also slice from another slice. Here we don't have an array here, but you can create more slices out of this slice. Okay, and also we can modify, we can make changes to this syntax. We don't always have to provide the low bound or high bound. We don't always have to provide the start index and end. We can leave one of them and the other range will be implied. So for this case, we are saying we are slicing from the first index, it's from 0 to 2. Okay, those things are implied here, and we can run this and see the example how it looks like. So we have 357 for the first, then 3. Three, 5 and 5. Here for this we have 357 because we are indexing from up from here up to here, from index 1 to index 4. So we are taking 1, 2 and 3. That's why we have 357. From this we have this 3, 5 and 7. This is the value that we have. Then we can slice it again, and when we slice it, we are slicing from the first position, from 3 to the index 2. So 0, 1, 2, and we exclude the 2, so we have 5. We have 3, 5. That's why we get 3 and 5. And here we take this slice and we slice it again. And we are slicing from the first. That's why we have 5 here. So that's how slicing works. And you can slice from an already existing slice. You don't always have to slice from an array. You can also slice from an existing slice. Now, in this example, we take a look at lengths of slices. So what we slice you can go of now right after. Slices out of this slice. slice. Okay, and slicing mixing we have from here to ending a function called print slice. What it does, it takes a slice of integer as a parameter, and what it does, it tries to print it. And how does it format it? It is taking the length of the slice, and it is taking the capacity of the slice, and it is then taking the slice itself, and it is printing all three of them in this format. Okay, that's what this function does, and we use it here. We create a slice using the literal syntax. We say it's a slice of integer, and we provide all the integer values, and then we do the print. We call the print slice function, the start elements. Print when we have is, well, let's imagine this is the backing array, because when you initialize a slice literal, then the length and capacity of the backing array is the same as the length and capacity of the slice. And I have we are go experiment is this, and we are going up till 4, 7. We exclude the fourth index. We have the capacity 6 backing array. Now what happens this? Now here this is the backing array, and we up of slice. When you are slicing, we go to the last element of the slice. Okay. Now what is the last element of the slice? Is 7. That's why we have 7 here. Okay. And what is the length here? Since we have this, and what is the last element? 13. So how many capacity length? It will have 0 value to print value of S. In this case, that data type case, this is, as you can see, length. As we already know, in this case, Go assigns the 0 value. So a boolean, it is false value of a slice. What will Go assign in will be 0. Since it is a slice of C, okay, this is what we get. For this println statement, we are getting S. If you try to print S, it is printing an empty array or an empty slice. The length is 0 and the capacity is 0. So for a 0 value slice, a slice which is declared without an initialization value, the length will be 0, the capacity will be 0, and it will have 0 elements. But the thing to focus here is the value of the slice itself, not talking about length or capacity or the print statement. The value of the slice will be nil. When we try to compare it, if S equals to nil, we get inside and we print this statement, because the zero value of a boolean is false, 0 value of an integer 0, and 0 value of an array is all the, let's say if it's an array like for integer, then the zero value will be 0, 0, 0, 0. Okay, this is the zero value of an array with size 4 and type integer. What is the zero value of a struct? So let's say, okay, let's come here. We have a struct, and here we have a is an integer, and b is a string. Now, what is the zero value of this struct? The zero value of this struct is a 0 and b as an empty string. Basically, in case of an array and in case of a struct, the zero value is that data structure with all the zero values of the elements, because an array is a fixed type with 4 pointers. We have slices, we have maps. And since we are talking about slice here, the zero value of a reference type, which is a slice, is nil. It's a very important thing to remember. The zero value of a slice is nil. Now we saw the first way to initialize a slice, which is the literal syntax. So in this case, we saw that we can declare a slice and we can initialize it like this. A, and we have integer, we have our curly braces, we have 1, 2, 3. Okay. And we saw we can declare and initialize a slice with this syntax, with the literal syntax. We also saw we can declare a slice using var and the name of the slice and the type of the slice. And for this, the value of the slice will be nil, the length will be 0, the capacity will be 0. For this, the length will be 3, the capacity will be 3. Okay, and the value will be 1, 2, 3. We have one more way where we can initialize a slice or declare a slice is using make. A make is a function, a predefined function. Make, M-A-K-E. It's a predefined function given by Go for initializing reference types. This is something to remember. Initializing reference types only. Okay. We can use make to initialize channels to initialize slice types. This is something to remember. Initializing reference types only. Okay. We can use make to initialize channels, to initialize slices, to initialize maps, all the reference types that we can use make to initialize, because we have a reason to use make instead of using the literal syntax. Why are we using make? So let's see that in this example. When we initialize a slice using make, what happens? So what we are saying is we are initializing a slice of A, and we are saying make a slice. Make, you can take it as semantically, whatever it reads like. You're saying make a slice of integer. You're saying make a slice of integer, make a slice of integer with the second argument. The second argument to the make is the length. This is how makes signature looks like. Make, it takes three things. First is the type. And what are we providing in the type? We are providing, it's a slice of integer. It is a slice of integer. Since we also use make to declare and initialize maps, to declare and initialize channels, so we have to explicitly say that it is a slice of integer. First parameter, first argument is a type. What is the second argument? Is the length. You can say what is the length of this slice going to be. Okay. now we already know that slices are dynamically sized. We will see how the dynamically sized mechanism works. But initially, you are saying initially the length should be 5. Okay, you are saying the length should be 5. Now there is a third parameter. There is a third parameter called capacity. We already know the mechanism of capacity. We still have not gotten the exact use case of capacity, but we'll get it soon. Now the third parameter is capacity, but by default, if you don't provide the capacity, it will take whatever the length is. So in this case, the capacity will also be 5. So now we have a print slice function. What we are doing is we are printing the length, the capacity, and the slice itself. Okay. Now, in the first case, what should it print? Now that we have the theory, before you run the program, we can visualize it for the first statement, for the first print. What we are doing, we're printing A. At this point, what's the state of A? The length will be 5 and the capacity will be 5. Okay, then now let's move on to B. What's B? Okay, now we are using make. What is the type? The type is a slice of integer. What is the length? Length is 0. What is the capacity? The capacity is 5. Now, you cannot provide a length that is greater than capacity. That is an error. Okay? That's something to remember. The capacity will be always same or greater than length. The capacity cannot be less than length. Okay? Since capacity represents the size of the backing array, so capacity will always be the same or greater than length. Okay. Now, this is the state of B. Now, when we call print slice, what should it print? It should print length is 0, capacity is 5. Also, for A, I forgot to mention what will be the actual slice print. In case of A, since the length is A and it is a slice of integer, ideally it should print, A should print 0, 0, 0, 0, 0. 5 zeros because the length is 5. What should B print? It should print an empty slice because the length is 0, so we don't have any slots to initialize it with. In case of A, the length was 5 and the type was integer, so the 0 value of a slice of integer with length 5 should be 5 zeros. Okay. Now C. Let's move on to C. We have C here. Now we are slicing C from B. What are the properties of B? You have length 0 and capacity as 5. Okay. And what we are saying, we are saying for C, we want to slice from the 0th index to the second index. Now C, now B has a capacity of 5. B has a capacity of 5. So let's imagine B has a capacity of 5. Now for C, B is the backing array. There is another backing array, but for C, you can imagine B is the backing array. What you're saying, we are saying starting from the first index. The first index is, we should have 0, 1, 2. Since we exclude 2, we have 0 and 1. We have 2 elements. Okay, we have 2 elements. Now, what will be the elements? Since the length is 2, we are slicing 2 elements. Length is 2. And it is a slice of integers, we should have the 0 value of 2 elements, which is 0, 0. Okay, the length is 2. And what will be the capacity here? The capacity of the backing slice is 5. And we did not slice, we did not slice from first index or second index. We sliced from the very first 0th index. That's why the capacity does not change. The capacity only changes when you slice after the first index. After capacity slices, not slicing from the second index. Starting from second index, it has only 2 elements. We don't really have index 2, but we have capacity of 5, so we can slice up to 5 elements. Because the capacity is 5. Okay, what you're saying, 2 to 5, since 5 is excluded, we did not slice from, is 3. See, for the first one, length is 5, capacity is 5, we have 0, 0, 0, 0, 0. For For the second one we have two zeros. We have a slice, which is a slice of string, and we are providing another slice, and that slice is a slice of string. So we are initializing with each slice, which is the text, in different positions. That's pretty much all there is. Initially, I said slices, whatever your intuition. Whatever it sounds like. Initially, I dimensional slices, whatever your print, some kind of matrix. And as you can see, we are printing a game of tic-tac-toe. Okay, and we can change the values using the x index and y index in different positions. That's pretty much all there is to it in two-dimensional slices. Whatever your intuition, whatever it sounds like. Initially, I said that slice is a dynamic. at this point, what's the state what we are doing? doing is we are printing the length, the capacity, and the slice. C did not an index. 2 did 2 as is a slice. We have two-dimensional arrays in a lot of languages, pretty much every language. In the same way, in Go also, we have two-dimensional slices. And if we print this, we should have some kind of matrix. And as you can see, we are printing a game of tic-tac. Extend a slice is a whatever it sounds like. Initially, I said that slice is a dynamic array. And dynamic means we can extend a slice, extend its length, extend its capacity, and add more elements, remove elements, all the dynamic properties that are useful in a real world application. That's why we use slice more often than we use arrays, because of their dynamic nature. Now, how do they work? How do we actually add more elements to a slice after we declare it? So this is how it works. This is the syntax. We declare a slice and we are using the var syntax. So at this point, the value of the slice will be nil, and if we print it, it will be an empty slice, and the length will be 0, the capacity will be 0. Okay, and if in the first print statements, we should get the length 0, capacity 0, and empty slice. What happens here? We are saying we are appending to this slice. It takes the slice had is provided to slice. Also has a concept called verydict function, where a function can take any number of arguments. Okay. Now append is a verydict function. You can pass any number of elements after you pass the slice. Okay. Now second, it can take one element like it is taking now, 0, or it can take any number of arguments. It takes two things. What it does is, first it checks the length and the capacity of the existing slice. Now what is the length and capacity of our existing slice? It is length is 0, capacity is 0. Now if that is true, and since we are trying to add more elements into that slice, but we don't have the capacity for it. Okay. The backing array that we are using in this slice, the array does not have enough capacity to it. So what append does, it assigns another memory location, another backing array whose length is 1 and whose capacity is 1, and it returns that as a return value of append. Now you are assigning it to S. Now what happens? S has length 1 and capacity 1. What happens here after that? Then at this point, S has length is 1, capacity is 1. Now this is what S looks like as of now. Now what we are doing, we are calling append again, and we are passing 1. We want to append the number 1 into this slice. We pass it, and append checks the capacity of the existing backing array. And since the capacity is 1, we are trying to insert another element. So we need at least 2 slots. So for that, append finds another memory location and it assigns another backing array. Now we have length as 2 and capacity as 2. And this is what the new slice looks like. And this is what we return, and we assign it to S again. Okay. Now at this step, this is what it looks like. And since we are inserting 3 elements, now append follows different algorithms to resize the existing slice. There are a lot of internal details there, but on a high level, there can be 2 situations. Either you are appending 1 element, or you are appending a number of elements. You are using the variadic parameter. Now to understand that, so let's go to our notepad. Now, as I said, there can be 2 cases. One, you are inserting 1 element, or 2, you are inserting variadic elements. Now, there are a lot of internal details, as I said, for resizing the slice inside the append function. Now we can actually take a look at how the code looks like, which resizes the slice using the append function. Now, if we go here, this is actually the code which does all the resizing of the slice and all. inside the Go programming language. You can see there are a lot of internal details here, and there is actually a function which is next slice capacity, the function to calculate what is the capacity of the next slice. You can see there is a threshold of 256, length of 256. It is smaller than that, it doubles it, otherwise it does something else and all. So there are a lot of things happening here, a lot of internal details. But to have else and all, these some of these rules. So the first rule is if it is a single argument, if it is a single element, we first thing we know, we use append to resize, to add more elements to a slice. So let's say we have a slice with length 0, capacity is 0. We have an empty slice. Now, if we call append, s equals to we take S, we pass it to append, and we add another element, let's say 1. What happens now? What append does in this case, this since this is a single element, what append does, since the capacity is 0 at this point, it checks the size of the element since this size is 1. So append finds another memory location for the new backing array, and it finds the pointer to that, and it assigns that new pointer, and that array will have a length of 1 and a capacity of 1. The first time we call append on an empty slice. What happens the second time? Now, this is what the slice looks like. We have 1 here. Length is 1, capacity is 1. What happens if we call append again? We call append again with S and number is 2. At this point, what happens? It finds, since the capacity was 1, we are trying to insert another element, so we need the capacity of 2. So it finds another memory location for the backing array, and it assigns the pointer to that, to the new slice, and now the length is 2 and the capacity is 2. We'll soon notice the pattern here. Again, let's try to append another element. Append S, and this is what the slice looks like in the previous step, 1, 2. Now S3. Now at this step, what append does? Since we have capacity of 2 and we are trying to insert another element, now we need slots for 3 elements. Now what append does, it tries to find another memory location for the backing array, and the length will be now 3, but the capacity will be the double of the previous one. So previously we had capacity of 2, now we will have the capacity of 4. Okay, so let's do one more time, then we'll see the pattern. Let's call append, then S, then we pass 4. Yeah, and this is what it looked like, 1, 2, 3, and we call it once more. Now we had capacity of 4. Now we are trying to insert another element. We only have 3 elements as of now. So the append does not do anything. It has enough capacity to assign one more element. So now length will be 4, capacity will be 4, and this is what the array slice will look like, 1, 2, 3, 4. Now what happens here? One more time. Call append, call S with 5. Now we have 4 elements, we have capacity 4, we are trying to insert one more element. Now we don't have the space for that. Now what append does? Now the length is 5, capacity is 8. It is 8, and this is what the slice will look like, 1, 2, 3, 4, 5. Now we can see the pattern. When we are trying to insert single elements, append will try to double the capacity every time there is no space. Every time there single element. First thing we know, we use append to resize, to add more elements to a slice. So let's say we have a slice with length 0, capacity is 0. We have an empty slice. Now, if we call append, S equals to, we take S, we pass it to append, and we add another element, let's say 1. What happens now? What append does in this case, since this is a single element, what append does, since the capacity is 0 at this point, it checks the size of the element since this size is 1. So append finds another memory location for the new backing array, and it finds the pointer to that, and it assigns that new pointer, and that array will have a length of 1 and a capacity of 1. The first time we call append on an empty slice. What happens the second time? Now, this is what the slice looks like. We have 1 here. Length is 1, capacity is 1. What happens if we call append again? We call append again with S and number is 2. At this point, what happens? It finds, since the capacity was 1, we are trying to insert another element, so we need capacity of 2. So it finds another memory location for the backing array, and it assigns the pointer to that, to the new slice, and now the length is 2 and the capacity is 2. We'll soon want of the previous one. So previously we had so 3, and the length will be now 3, but the capacity will be trying to insert another element. Now we need slots for 3 elements. Now what append does, it tries to find another memory location for the backing array, and the length will be now 3, but the capacity will be the double of the previous one. So previously we had capacity of 2. Now we will have the capacity of 4. Okay, so let's do one more time, then we'll see the pattern. 4. Append will try to double the capacity up to, as we saw here, up to one pattern. And if you want to see an example for that, here we are declaring a slice with 0 var capacity, and this, it is 1. In the second iteration, it inserted another index and having to assign a new memory. And then now when we leave this, let's run this, and we can see, and to store one more, and again will try to double the capacity. Internal calculations will keep happening when you start with a slice. Let's imagine there is a scenario like this, when you know beforehand that this then it matches in work. Every time reallocation happens, but that you can do to prevent append from doing all this extra work is this. Instead of initializing S like this, what you can do, you can remove this and you can use the short declaration form, and here you can use make. And you already know, if you use make, you can define a length, and don't define length as 5 and capacity is 5. It will pre-fill all those places with empty zeros. We don't want that. That's why we are saying length is 0, but capacity is 5. Maximum we'll have 5 elements, but for now, give us an empty slice. What happens if you run this? Is 5. Last, we are going to append 5 elements max, and we just prevented append, the function, inbuilt function append, from doing all those extra calculations every time there was a shortage of space. So this is something you have to remember, that we'll use, especially this syntax, that if we know beforehand what is going to the maximum size of a slice, we can use this syntax to pre-assign the extract, we use a traditional iteration, and then we can print the index and the value using the index access method. This works, but Go provides us another construct. It's called range. And using range, you write a for, and with each iteration, Go returns two values. First one, the index, and the second one, a copy of the value, not the value itself, a copy of the value. This is something you have to remember. If you make any change to this value here, it won't show up in the original slice because this one is a copy in each iteration. And you can access the value of I and B here. And if we try to print this, we'll get this 0, 1, 2, 3, 4, 5, 6, 7. And if you don't want to use the index, then you can use the underscore. And if you don't want to use the value, you only want the index, then you can leave it apart. Okay. And if you want to take a look at the index, then you can leave it apart. print a dot here, whatever your intuition, whatever it sounds like. Initially, I said that slice O provides us one more construct to loop over slices. In apps, then we can take a look at who don't want to. And if you want to take a look at some examples of slices in real world apps, then we can take a look at Spider. And we can see we have a lot of use cases. Here they are using initialize the slice in the same line. We have some make based syntax to initialize a string slice with length 31 and capacity 31. And similarly, there are a lot of use cases everywhere in the code. Slices are one of the most common used data types in Go, and you will see a lot of examples everywhere. Okay, here we have a range over slice. They're accessing the value of title in each loop, and they're doing something with it, and a lot of examples like that. Now, the next data type that we have is maps. Go offers a implementation of the data type hash map, which are also called dictionaries, hashes, hash maps in other languages. Go also has a similar implementation. It is called map. And map, a typical structure of a map is it has a key, which is mostly string, but you can starting index, and in